Hey, I'm Joseph from Alchitry, and in this video, I'm going to cover the ins and outs of the ins and outs on an FPGA. I'll often get emails asking about the ins and outs, aka I/O capabilities of the FPGAs we sell. Things along the lines of, how many serial ports does the AU have? These usually come from people who are familiar with microcontrollers, but not FPGAs. Microcontrollers like an Arduino or Raspberry Pi have a central CPU and a bunch of built-in peripherals like serial ports. If you dig into the datasheets for one, you'll find out exactly how many they have and what pins they connect to. Many newer microcontrollers will even let you select between a handful of pins that each peripheral can be routed to. For the most part, FPGAs just have generic I/O pins. They don't have things specifically like serial ports. After all, FPGAs are programmable hardware, and when you need something like a serial port, you just program it in wherever you need it. This is true for the vast majority of signals, especially if we limit ourselves to the standard 3.3 volt logic levels. Let's take a look at what it takes to hook up a serial port to some pins on an FPGA. Here I'm starting with a new project that includes just the basic boilerplate for the AU. If this doesn't look familiar to you, check out our video about creating your first FPGA project by clicking the card up here. You can see we already have two signals, USB-RX and USB-TX, defined for our module. These signals are intended to be connected to the USB serial interface chip built into the board. But how do the tools know which pins to use? That's where the constraints file comes into play. We can open up the alchitry.acf file on the left. This file specifies the pinout for all of the signals of our top level module. Most of the lines here are standard pinout declarations. Take a look at the last two. They start with the pin keyword and are followed by the signal name and finally the pin name. The pin names of USB-RX and USB-TX are special pins that correspond to the serial port signals on the board. There are a handful of special names such as LED, reset, and clock, as you see in this file. However, most of the pin names that you will normally type take the format of the bank letter followed by the pin number. Take a look at the AU. There are three connectors on it. The small 50-pin connector in the top left is the power/control header. It has signals for power, programming, and other special control signals. The top 80-pin connector is bank A, and the bottom 80-pin connector is bank B. These are where most of your signals are routed through. Looking down the side of a header, the pinout takes the format of ground, pin, pin, ground, pin, pin, ground, pin, pin, ground. This is done for signal integrity. The name of each pin is the bank letter followed by the pin number. For example, the first I/O pin on bank A is A3. What would have been pins A1 and A2 are actually grounds. If we wanted to route our serial signal to the pins on the connectors instead of the internal serial interface, we would just change the pin names from USB-RX and USB-TX to something like A21 and A23. Since these are just basic signals, we can route them to any I/O pins on our board. The BT is a little unique in that it has banks A and B on both the top and bottom, but they're fully independent. To specify which side you're connecting things to, you use the side attribute. Looking back at our basic constraints file, we can see the side attribute is set to top for all of the pins. The syntax with the attributes surrounding the pin declarations is just shorthand for putting it on every single line inside the block. We could have written the pin declarations standalone like this. Because the top and bottom of the PT are fairly similar, this makes it possible to select which side you're attaching a board to simply by switching one value. For example, if we had a project using an FT+, if we wanted to attach it to the bottom instead of the top, we could open up its constraint file and change top to bottom. Of course, it would be too easy if there weren't some exceptions to pin usage. So let's dive into where things get interesting. The most important special I/O pins to be aware of are the clock-capable inputs. These are our I/O pins that connect to special routing resources inside the FPGA, which are designed to distribute a signal throughout either the whole FPGA or large regions of it efficiently. This is critical for any signal that clocks part of your design. Note that you don't need clock-capable inputs for relatively slow clocks, used by some interfaces like SPI. These clocks can often be treated as standard data signals, and they don't need to clock flip-flops directly. As a rule of thumb, if a signal is less than something like 10 MHz, you can usually get away with not treating it as an actual clock. You can clock your design off the 100 MHz built-in clock and synchronize the slower signals to that. It's also worth noting that any pin can be used to output a clock. There's a little bit of trickery involved due to the way that signals are routed internally, but it works for any pin. Different manufacturers call their clock-capable inputs slightly different things. For example, Lattice calls them GBIN for global inputs, while Xilinx calls them MRCC or SRCC for multi-region clock capable or single region clock capable, respectively. For the most part, you can treat MRCC and SRCC pins as the same thing. Either can be routed to the global clocking resources, and they differ only in their local clocking resources. On the Alchitry boards, clock-capable pins are placed in the same places on the headers. That is, pins 41, 42, 47, and 48 on each header. Bank A is always fully populated. However, Bank B is partially populated on the CU and AU. The PT, with all its extra I/O, has 3 additional clock inputs on the top side bank B and a fully populated bottom side bank B. On the AU and PT, you may have noticed that both pins of a pair are labeled MRCC or SRCC. However, internally, there's only one clock connection, and it's connected to the positive pin in the pair. They're both labeled this way to indicate that they can accept a differential clock signal. This rolls into our next topic nicely: I/O standards. While most microcontrollers only support a single I/O standard, FPGAs often support many. Which I/O standards are supported depends not only on the FPGA, but also the voltage that the I/O pins are powered with. The most common standard you will likely use is LVCMOS 33. This is your basic 3.3 volts single-ended logic. It's also the only standard supported by the CU. The AU and the PT support many more. Page 98 of Xilinx's doc UG471 details all the available standards and their voltage requirements. Let's take a look at some of the more common ones. LVDS, specifically LVDS 25, is a common standard for high-speed signals. LVDS stands for Low Voltage Differential Signaling, and then, as the name suggests, it's a differential standard. That means instead of looking at the voltage of just a single pin, it compares the voltage between a pair of pins. If the positive pin of the pair has a higher voltage than the negative pin, it's considered a 1. However, if the negative pin has a higher voltage than the positive pin, it's considered a 0. LVDS comes in many flavors, and you need to check the datasheets of the 2 devices that you're connecting to make sure that the common mode and the differential voltages are compatible. For the AU and the PT, page 11 of Xilinx's doc DS181 has all of the details. As a quick example, let's take a look at the LTM9008, a high-speed analog-to-digital converter that has an LVDS interface. On page 5 of its datasheet, we can see that its common mode output is between 1.125 volts and 1.375 volts. And its differential output is between 247 millivolts and 454 millivolts in 3.5 milliamp mode, and 125 millivolts and 250 millivolts in 1.75 milliamp mode. Looking at the Xilinx datasheet, we can see that we need the common mode voltage to fall between 0.3 and 1.5 volts, so we're good there. The differential voltage needs to fall somewhere between 100 and 600 millivolts, so we're also good for both modes of the ADC as well. However, the 3.5 milliamp mode would give more margin, so it would probably be a better choice. Any differential pair on the AU or PT can accept an LVDS input. However, only pins that have a VCCO of 2.5 volts can use the built-in termination or be used as outputs. VCCO is the voltage used to power that group of I/O pins. Most of the pins on the AU and PT are always powered with 3.3 volts. However, a group of pins on each board has some extra circuitry that allows the VCCO to be switched between 3.3, 2.5, or 1.8 volts. The 2 signals, VB Select A and VB Select B on the control header, select this. If you leave them both floating, VCCO is set to 3.3 volts. If you short them together, VCCO is 2.5 volts. If you pull VB Select A high and VB Select B low, VCCO becomes 1.8 volts. With the tri-voltage pins, you can use I/O standards LVCMOS 25 or LVCMOS 18 for 2.5 volt and 1.8 volt I/O respectively. This means that you can interface with devices that use 2.5 volts or 1.8 volts I/O directly without the need of an external level shifter. However, you can only do one of these at a time, and just make sure that the VCCO is set correctly for the I/O standard that you're specifying. Failing to do this could damage the FPGA. 2 pins on the AU have their VCCO fixed at 1.35 volts. These are extra pins from the group used to connect to the RAM on the board. Just be aware of this special set when designing your pinouts, as they are not 3.3 volt tolerant. Besides LVDS, another common differential standard is TMDS, or Transition Minimized Differential Signaling. This is the standard used by HDMI. We can take a look at the HD's constraint file to see how it's used. Here we have 2 groups of signals, some using the LVCMOS 33 standard and some using TMDS 33. TMDS is convenient in that it requires a VCCO of 3.3 volts, so any pins can be used as inputs or outputs. There are other attributes that can be applied to I/O pins other than the standard attribute. You may have noticed the frequency attribute in the basic constraints file earlier on the clock signal. The frequency attribute is used to tell the tools that a signal is a clock and what frequency it's going to oscillate at. This is critical for timing and something that we'll cover in a future video, so make sure to subscribe for that. The pull attribute can be set to up, down, or keep on the AU or PT to enable pull-ups, pull-downs, or a keeper circuit. The CU only supports up for pull-ups. A keeper circuit will switch between a weak pull-up or a weak pull-down depending on what the current state of the pin is. Some attributes are supported on the AU and PT, but not the CU. First, the drive attribute can be used on some I/O standards. For LVCMOS, it can be set to 4, 8, 12, or 16 milliamps. This is how hard the I/O pin will be driven and defaults to 12 milliamps. The slew attribute is used to set how fast a pin will switch states. It can be set to slow or fast, with slow being the default. Using fast may help with some high-speed signals, but it causes more power consumption and noise, so it should be used carefully. The diff term attribute is used to enable internal differential termination on a signal. It can be set to true or false and defaults to false. It's most often used on LVDS 25 inputs using the tri-voltage pins with a VCCO set to 2.5 volts. Enabling it when VCCO is not set to the correct voltage may damage the FPGA. Since we're taking a close look at the I/O pins, it's worth taking a quick glance at the GTP pins on the PT. GTP is an implementation of Xilinx's multi-gigabit transceivers, or MGT. That allows for LVDS signals as fast as 6.25 gigabits per second. These pins are located on the bottom side bank B connector, and they can't be used for anything else. These require substantially more effort and care to be used correctly, but they can be used to implement high-speed interfaces like PCIe 2.0. If you're really getting into the weeds with your FPGA design, there may be some constraints that you need to specify that aren't directly supported by the Alchitry constraints format. In those cases, you can use a native block to inject native constraints. These are XDC for the AU and PT, and SDC for the CU. The constraints inside a native block are copied mostly as is into the final constraint file, with the exception of some helper functions. The native constraints expect you to use the name of the pin on the FPGA and not the Alchitry board's pin name. To automatically look one up, you can use the ACF pin function. For example, if you have an AU, then ACF pin A3 for the first I/O pin on bank A will be replaced with N6. This is the name of the FPGA pin. The other helper function, ACF port, is used to convert your top-level module signal names into their native names. Hopefully this video gave you a good foundation for the I/O on an FPGA. Make sure to check out the Alchitry constraints reference linked below in the description for all of the details. If you found this video helpful, don't forget to like, comment, and subscribe to see more videos like this in the future. As always, thanks for watching. Transceivers. Yeah. Well, oh my God, I'm gonna call that